Hello and welcome to another episode of Math Made Bearable, or Made Almost Bearable. This is Frank Kelly. Today we're going to talk about something called the birthday problem. It's a famous problem in probability theory. And the problem is, how likely is it that in a group of n people, at least two of them have the same birthday? Now, of course, if there are at least 367 of them, I think you can see that at least two of them have the same birthday, so the problem's not interesting for very large groups of people. Keep in mind that when I say same birthday, I just mean same day, same month, like July 2nd or something. I don't mean July 2nd, 1902, okay? So there's the birthday problem. Well, the way I've said it, it's actually very hard to solve directly. So let's just say this problem is too hard. And let's think about a little bit simpler problem that's, it turns out, related to this in a very strong way. And this problem is, how likely is it that they're all different? How likely is it that they're all different? That'll erase here a little bit. The birthdays are all different. Now think about it for a minute. Suppose I could figure that out. Suppose I could calculate that and figure out how likely that was. Would I have the answer to my original problem? Well, look, either they all have different birthdays, or there's at least one match. So the probability of this, that they're all different, plus the probability that there's a match, they must add up to 1. So the probability of a match must be 1 minus the probability they're all different. So if we can do the all different problem, subtract it from 1, we'll get the answer we're looking for. Very often in mathematics you say, I can't do the problem they gave me, so I'll do a different problem. And if I can do that different problem, I'll be able to do the one I started with. So let's see if we can do that. And let's imagine a sort of a simple case. Suppose n equals 5. How can I have, that looks like an S, n equals 5. How can I get the probability that 5 people all have different birthdays? Well, first of all, let's forget the pesky February 29. It happens to be Rossini's birthday, and that guy's younger than I am, even though he lived in the 1700s. I hate that. Anyway, how could we do this? Well, let's see. Let's see if we could count the ways that 5 people could all have different birthdays. Well, let's look at person 1. How many possible birthdays can person 1 have? Well, any one of 365, right? Now the second person can have any birthday, but we don't want him to have the same, or her to have the same birthday as the first person. So there's only 364 possibilities for the second person. For the third person, has to be different for both of those, so only 363, and then 362, and then 361. So there's all the ways that 5 people could have different birthdays. Now let's remove the restriction that all the birthdays are different and just ask the question, well look, how many ways can 5 people have birthdays? Well, they can each have any day they want. That would be kind of cool if you could pick your birthday, but anyway. So that ratio is the total number of ways that their birthdays are different over all the ways that they could have birthdays. So this is the probability that they're all different. Now if you calculate this, multiply it all out on a calculator, this is practically 1. It's 0.9 something or other. So for 5 people, it's pretty unlikely you're going to get a match. So the match is 1 minus that. But now suppose you let n get larger. Imagine n is oh, let's just say 23. Now what's the probability of a match? It's 1 minus 365 times 364 times 363 down to what? Where do I quit? Well, you might think it's 342, but it's not. It's 343, and you ought to figure out why that's true. And then the denominator is going to be 365 to the 23rd power. Well, that looks pretty tedious to calculate, but I guess you could do it. And it turns out that the answer is very close to 0.5. So that means if you have 23 people, it's like flipping a coin whether they all have different birthdays or whether there's a match. And when n gets bigger than 23, that means that the probability of a match goes up, gets bigger than 0.5. If you let n be, say, 50, the probability of a match is practically 1. Just about 1. And in fact, among our presidents, for instance, there have been 43 people, I think, who've been president of the United States, and it turns out 2 of them had the same birthday. 2 of our greatest presidents, Harding and Polk. So see, probability can teach you stuff you didn't expect was true. See you next time on Math Made Almost Bearable.